All right, rock and roll. Can everybody hear me all right? There's quite a bit of lag in my streaming service as looks like it's having some issues. It says excellent connection, but it doesn't look like an excellent connection. Oh, sweet. Excellent. Can you guys see me? Sweet. Excellent. Well, I don't know why it's showing. Oh, 5x5. I got you. Cool. All right. So Tesla just came out with a patent, and I don't have time to make a full video on this. So I'm just going to jump in. Fuck it. We're doing it live. What this patent solves is the triangle problem that I've brought up in my previous videos. I'm just going to see if I can bring up an image of this. This is good practice for battery day, by the way. I needed to test this anyways. So I'm going to see if I can show my desktop. Hopefully that's working for you guys. I'll check back here in a second. All right, so the triangle problem that I showed in my battery day video, I'll just let that flow through the system to you guys and then check to make sure that you can see it. Cool. Somebody said yes. I'm assuming that's to the triangle. All right. So the limiting factor for one of the limiting factors for batteries is the competition between discharge and charge rate, cathode thickness, and cell volume. You can't do all of those things at the same time. If you crank the discharge and charge rate up too high, it creates too much heat. If you make the cathode too thick, it creates too much heat. And if you create a cell that's too large, that creates too much heat. Of course, discharge and charge rate, those are positives. The reason why you'd want to have a thick cathode is because if you just increase the cathode thickness by 25%, you get about a 10% specific energy increase. So that would be going from like 300 to 330 watt hours a kg. Cell volume, if you just increase the cell volume by a small amount, say when Tesla went from 18,650 to 2170, that small increase reduced the number of cells they needed to create by about 30%. And we have 30% less cells, you have 30% fewer welds, 30% fewer separators, 30% fewer cell cans. It's just it makes it a lot cheaper and easier to manufacture the battery pack. Now, I said that there was two ways to shrink the triangle to try to fix all these things at once. The first was for Maxwell's dry cell technology, and what that does is it uses a lot less additive material, and because the additive material isn't being corroded by the liquid solvent, it has much lower resistance. And because it has much lower resistance, electrons can get in and out of the cell much more quickly, and there's less heat and less resistance. There's one way to combat it, and the other way to combat it is to improve the thermal management system of the battery. So with all that and that's our problem that we're trying to solve. And those are the only two solutions that I could come up with. I'm going to just return this camera to me. Okay, webcam. And I'll just bring this back up again. Cool. Let me know when you guys can see me again, and then I'll bring out my props. You're gonna love this. I'll just wait until you can see me. It takes about 15 or 20 seconds. Oh, let's see here. Let's wait until you guys confirm that you can see me. Then I'll bring up my examples. All right, cool. Thanks, Levin. You've been really helpful. All right, so this is my model for a current battery cell. I've used a toilet paper roll. This is the cell can. I'm just going to take the cell can and throw it away. And currently, what happens is, in order for the, I'll just move this around here. In order for the electrons to get in and out of the battery cell, they have to go through one of these little tabs. And that's a huge ass bottleneck. If you're an electron and you're in the center of this toilet paper roll, you have to go through that maze, all those different spirals to get out of the battery, or in this case, our toilet paper roll. And then when you get there, there's a big bottleneck in the form of these tabs. Well, what Tesla's decided to do is the best part is no part. So they just get rid of these. Now, how is this cathode or anode material, how's it going to get to the collector and get to the edge of the battery if you don't have those tabs? Oh, first off, you can see that the black goes pretty much all the way to the edge here. That's the cathode material. What they've done is they create an offset at the top of the battery cell. So all you have to do is just put some conductive adhesive on the top of the bottom, jam it in the cell, boom, all the electrons can access from any point, from any layer. And you don't have to fiddle around with that stupid little tab and weld those fickle little pieces of metal to each other. So A, that makes the manufacturing a lot easier. And B, if you're an electron trying to get through all that mess and all that maze, you're bumping into a lot fewer other pieces of material. And if you're bumping into fewer pieces of material, it's creating less heat because there's less friction. So that adds a way that we can solve our triangle problem. So with that in mind, I hope that explanation made sense. I haven't had a chance to read all the comments yet. Anyhow, I'll start reading these comments. The implications of this. I haven't had a chance to sit down and process this, but it looks like what this means is Tesla should be able to greatly simplify the manufacturing process by making the cells smaller, by making the cells bigger. So they need fewer cell cans, fewer tabs, less tab welding, fewer separators. It's just all of a sudden the amount of the number of pieces of each material they need to create these battery cells and battery packs could be cut by 30, 50, maybe even like 70%, depending on how big they make those battery cells, how big they make the diameter. Because the rumors I've heard are 40 millimeters. I don't know if that's correct or not, but this makes it much more likely. It makes that rumor from a possibility to, oh yeah, this is a pretty good chance that they're going to increase the diameter of the cell. Now, what it also does is it allows for increased discharge and charge rates because there's less heat generated by that. People say they look like little silver beer cans. What else? Charge, discharge rate, energy capacity. Yeah, increased energy capacity because whenever you have a battery cell, if you keep that can thickness the same and you increase the internal volume, the proportion of this paper to, metal and metal or paper, the proportion decreases as the cell gets bigger, so you get more energy capacity per given volume. Yeah, so you should be able to increase the energy density and potentially increase the cathode thickness. If they can even increase the cathode thickness by like 10%, that's, they'd be getting another 3, 4, 5% specific energy capacity. I mean, this is really cool. I was hoping that Tesla would unleash something straight out of left field that I hadn't anticipated, and this is it. This is awesome. Let me read these comments again. Tesla will use toilet rolls for the new battery cells. Thanks, Lars. Yeah, what the response before when people were asking me if, and this is to Steve Bowers, would this shorten charging time? Oh crap, did I forget to put on monetization? I think I did. Oh well, if you want to support me, you can go to Patreon. Damn. Oh well. Oh, wait a second. Oh no, there's a little icon there. Yeah, so previous when people asked me if Tesla would be able to shorten charging time with this new cell chemistry, my answer was, well, it depends on how they engineer it. Well, it still depends on how they engineer those battery cells, but it makes it much more likely that they can do the energy capacity, discharge and charge rate, and simplify manufacturing, do all of those instead of just one or two of them. No, I haven't heard any updates, Perry, on any updates when or if Battery Day is still this month. I haven't heard anything to the contrary. The cell voltage, I'm expecting 4.3 volts because that's all of Jeff Dahn's research was done at 4.3 volts. If I get a chance before Battery Day, I'd love to make a more in-depth video instead of using toilet paper rolls. So, yeah, but I'm just, after the Hyperchange interview, I have a number of people asking me for interviews. In fact, I'm going to have another one with EV Stock Channel here in a couple hours. So I'm busy. And then on top of that, I have work. So I'm on my lunch break. Oh, the battery will still need cooling. But this reduces the engineering demands on the cooling side of things. Yeah, we found another use for toilet paper in the pandemic. It doesn't appear that there's any trade-offs. Hey, thanks, Brent. Much appreciated. If anybody else, I'm going to just scroll up here and see if anybody else did made a donation and I didn't pick up on their comment. I feel really bad if I did. No, that's the first one. Cool. I'll just bring this screen up here again. Okay. Hey, no problem, Asimo. Hope I said that right. The battery quartz. In terms of series or parallel, I'm not sure. It depends on that pack design and if they've eliminated modules. Oh, wow. Hey, thanks, man. Okay, I'm getting a request to do the toilet paper demo again. I'll have to... I threw the pieces of paper on the floor to be dramatic. Hold on a second. I might have to make another cell tab. Just reinsert here and put our electrode tab back for the top. Make another one for the bottom. Keep losing my video here. I'm glad you guys can see this because it's not showing up on my end. Okay. So. All right. I'll do this once more for the people that have recently showed up to the chat. So this is an example of what a battery cell is currently. like. This is the cell can, and if we take off the cell can, we can see that there's the tab on the bottom for the, I don't know if it's the cathode and the anode, but anyhow, one is positive, or this will be the negative and this will be the positive. And this is actually attached to the cell can itself, and that's your entire negative. Now the one on the top, the positive is actually isolated with an insulated material, so that way it's separated from the can itself, so that you have the positive and the negative. So in order for the electrons to get out of this, they have to weave their way through all these different loops in the toilet paper roll, or the jelly roll, as it were. And what Tesla's decided to do is just remove these. So now we're left with a jelly roll, and how do we get the electrons out of that? And the electrode material, you notice, is all the way up to the edge. What they've done is they've just offset this. You put a bit of conductive material in each end, you just pop it into the battery cell. It's a little bit more complicated than that. In the patent diagram, there's about 5 or 6 different ways where they can connect the top and the bottom to the cell cap and to the cell casing itself. I haven't had a chance to look through all those, but they have lots of options available too. And this is just like, I don't know why nobody's done this before. It's freaking obvious. It's just so much simpler and so many benefits to it. So, yeah, once again, with a design like this, it's a lot easier for the electrons to exit and enter the can. Better discharge rates, easier cooling, less heat generation, higher specific energy, just from that little tweak. The best part is no part. Anyhow, I hope I explained that as well as I did before, if I did explain it well before. Thanks, Patrick. I'm going to scroll up and check out these comments because I was focused on, I can't do more than one thing at once. Okay. Curacao. And thanks, Float Sam. Patrick Johnson, thanks. I'm going to see if there's any other questions here. How many gigawatt hours for pilot cell line annually? Ooh, that's a good question. It depends on if the pilot cell line that they're building in Fremont, if they're building it in Fremont, if it's, I'm assuming it's just for the Plaid Model S and X. I hope we get these batteries that soon. Galileo Russell has a theory that it's just a pilot line just for show, and but I think those batteries are going to be used for something, and I think they're going to validate the cost model with the S and the X. Now, I theorize that it would be 5 gigawatt hours for the pilot line, based on the research I've seen. Thanks again, SMO. I'll answer your question in a second. But at a very minimum, it's going to be at least as much as Panasonic's lines, which I think is about 3 gigawatt hours. But the thing is, people are saying that this could go up to 10 to 16x what a current cell line is. So that would be 30 to 45. Yeah, something like 30 to 40 gigawatt hours is the potential for one line. Now, I think that's absolutely insane. I'm not in that camp, but I would say it would be, if you're going to do a terafactory, I think you're going to need lines that are at least cranking out, 10, 15 gigawatt hours. You'd also have some space savings there, so that would factor into the mix. And it looks like Tesla's factories are getting bigger. There's really no way to know. But yeah, I'd like to see a minimum of 5. 10 would be great. Anything above 10 is absolutely, that's in the stratosphere. And yeah, goodbye every other auto OEM. Tesla is talking about 250 kilowatt hour charging for Model 3. How fast could we go with these new packs? Any speculative predictions? Well, let's take a look at what diagram is that in? I have to have a catalog of files in my head. I'm just going to try to pull that up and show that on my screen. I'll just bring up the original white paper that Maxwell put out a couple of years ago. It's in my research folder. Okay. Research. Maxwell Tech. Here we go. All right, I'm going to share my screen. Let me know if you can see that. I'm just going to give a few minutes for that to kick in. And expand this so you guys can get a better look. Jump back to this and see if you can. All right, let me know when you can see that. When you can see my desktop. No comments. Hope this is still working. Can you guys still hear me? All right, cool. I'm going to go back to my desktop. All right, sweet. Here we go. So this is a dry-coated electrode or dry-coated cathode versus a wet-coated cathode. Now, a 0.1 discharge rate is like, that means charging or discharging in 10 hours. So that's really slow. And 0.2 is charging or discharging in 5 hours. 0.5 is discharging or charging in 2 hours. And this is where you see a massive difference between the dry-coated cathode and the wet-coated cathode. You can see that for if you charge or discharge within an hour, the dry-coated cathode retains much more of its capacity. Basically, the wet cell, as you start draining it or charging it, it heats up, you get a lot more internal resistance, and the capacity at that point is reduced considerably. And it looks like by about 30%, what is here, 50 versus 90, it's about 40% difference, or 30% difference at least. So I imagine that continues to get even steeper as you move towards, like a half-hour charging time. So I would think you'd be able to double the charging time. It really depends on how they engineer these cells. And it's also dependent on how much power that those superchargers can put out. I would think that with this Maxwell dry electrode technology, as well as this new tab technology that allows the energy to get in and out of the battery cell more quickly, that you'd be able to at least double the speed that you get the electrons in and out of the cell. There might be another factor there that I'm not aware of, but yeah, I think it would max out the current V3 supercharger, and you might need a V4 supercharger to fully take advantage of it. But at least you'd be able to utilize peak charging power for longer. I'll just go back to the chat now. All right, cool. Capacity retention basically says at that given point in time when you're charging and discharging the battery, how many electrons is it putting out? I'm just going to go back to, because I think some other people have donated some money. I'm just going to make sure I answer their questions. Okay, so I answered Asimo's question. Tesla keeps rethinking everything. They're lengthening the leader. Yeah, absolutely. Tesla is definitely with this. I mean, it looks like Tesla has been incubating half a dozen or a dozen technologies over the past decade. And I think they knew well before they acquired Maxwell that they were going to start building their own cells. And they've been engineering this stuff, waiting for everything to come together. And now that all the pieces have come together, they're going to implement technology which is not just slightly better, but a revolutionary change in batteries rather than a step change. Okay, I'm just going to go down to the next comment. Do you think the delay for Tesla in integrating Maxwell was them wanting to do many changes at once? Well, it's interesting. In the negotiations when Tesla was trying to take over Maxwell. They said, hey, if you guys don't jump on this, we're going to go do our own thing. I think Tesla had an internal timeline for when they wanted to do their own batteries, and Maxwell is icing on the cake. But I think when they were in those negotiations, they were being honest. I think Tesla had, like, we have 4, 5, or 6 innovations in our, little treasure chest of innovations. And even if we don't go with Maxwell, it will still make us the leaders in the industry. And so I don't think they were bluffing during those negotiations. I hope that answers your question. I think it was just a stroke of luck that Maxwell managed to get their technology working at the same time. And Tesla would have seen the Maxwell technology coming for probably 5, 6, 7 years, because all of them are on a board called the Battery 500 Consortium, and J.B. Straubel's on that, and he would have been monitoring Maxwell technology to see how their technology is developing. Yeah, we're talking about a Tony Stark change. All right. So many good questions here. Mega How To Man asks, are they going to put Panasonic out of business? No, I don't think so, because my view is, as long as your batteries are better than fossil fuels, then you don't have any competition for a good decade from now. It doesn't matter if Tesla's technology is 5 or 10 years ahead of everybody else. What battery makers are competing with is the fossil fuel industry. And as long as they can provide a better alternative to that, then I think they'll continue to thrive for the next decade. After 10 years or so, then I think there'll be some competition in the market because there'll be less market share. Okay. Yeah, I'm tempted to buy more stock too. I probably should have mentioned this in this videos. I don't know if it's relevant or not. My focus is mainly on technology, so I don't think I need to let everybody know what investments I've made. But I started investing back in 2016. There was an interview with an analyst named Andrea James, and to this day, I still think she's the best analyst that was ever on Tesla. And she was interviewed by Dave Lee on investing. I think it was like August 9, 2016, something like that. The next day after watching that interview, I bought my first shares of Tesla stock. The reason for that is because she said she got a tour of Level 2, and she said the things that they were doing on Level 2 in Tesla and their secret skunk works were so amazing that it almost made her cry. That's how amazing they were. So I bought stock the next day. I continued to buy stock all the way through the dips last year. And it's tempting to buy more at these prices, but I think the market's going to take a hammering. But I have confidence in Tesla over the next few years. John G. I haven't tried. Thanks, Holter. I'm curious about battery players. I'll just read this out. I know you're curious about the smaller battery players. Have you tried buying Nano One stock? It looks to be fairly illiquid. I haven't tried buying Nano One stock because I haven't been convinced that they actually have a customer yet. I'm confident in their technology. I think what they're peddling seems like a good product, but there's a lot of people peddling that product. CATL has fully commercialized single crystal cathodes in China. They're way ahead of us, way ahead of the Western world in that respect. But I think what Tesla's bringing to market is going to shock the world, at least shock the people in the world that care and know the significance. And I haven't done much financial analysis on Nano One. It looked like they had a pretty good balance sheet, but I haven't done any deep dives. I'm not a financial analyst. Let's see here. What would be the discharge capabilities for these new batteries? I answered that a little bit ago. Yeah, it could increase the charge and discharge capabilities. How fast do you think they could get the... I don't know. It depends on if they're, how much kick those cold gas thrusters have that they're going to be putting into it. Anyhow, I feel like we're getting a bit off topic. I want to try to keep this somewhat tight for anybody who stumbles across the video after this. If you have any other questions about this this tab technology or batteries in general, let me know. Otherwise, I'm going to wrap it up and sign off. You're welcome, Justin, and thanks for your support. It's so good to see so many names in the comments section here. People that I've interacted with in the comments. I try to talk to everybody. So let's wrap this up. I'll give a quick summary. What Tesla is doing with this patent is they're creating another way to reduce the heat that's generated by batteries. And what that allows for is greater specific energy capacity because you can make the cells larger. It allows for greater... one second. I'll start again. My brain's starting to cook. I need some lunch. So, I have to bring up my triangle again to refresh myself. No, it'll take me too long to find that. Anyhow, the new tab patent will allow the electrons to exit and enter the battery cells more quickly, which means less heat, which means they can increase the cell size, which means easier manufacturing. It also means greater discharge and charge speed and greater specific energy in the battery cells. Now, how they implement this is another story. You can engineer battery cells to have certain characteristics. If you make the cathode super thick, then you can have much higher energy density, but then you generate more heat, etc. But this makes it likely that they can do all three of those things at once. Thanks, Halter. And that's me. I'm signing off. It's time for me to get some lunch. Thanks for tuning in.